This is A2Pure Maths. We are towards the end of our unit on integration, and we're now looking at the practical applications of differential equations. So it says in some questions that differential equation may be given, but in others it may have to be instructed or set up from the information given. Just a few notes on that. So if the rate of growth in a population is said to be proportional to the size of the population n at any given time t, this can be stated mathematically in the following way. So the rate of growth means how this changes over time, and that is proportional to n. The way we would deal with that is that dn by dt is equal to kn, where k is a constant. And then to solve, dn by dt equals kn. We would separate out our variables, anything with an n to this side, anything with a t to this side. So we would of course then have dn over n equals k dt. Integrating, we'll fit in, I think we'll fit in here, okay. We have 1 over n dn equals the integral of k dt, and that gives us then ln n equals kt plus c, and in that case then that'll be our general solution for that one. Sorry about that. In contrast to this, if the rate of cooling, so if it's going down, to be honest it's very similar, but we'll follow through this one anyway, so you can see where it's coming from. So contrast to this is proportional to the excess temperature theta at any time t, then it can be expressed as minus d theta by dt. You don't really need the minus, but sure, we'll have it in here anyway, why not? And it's negative because it's decreasing. Minus d theta by dt equals k theta, and then d theta by dt equals minus k theta. So to solve this, again we would separate out our variables. So I would keep the k over here, I would divide through by the theta, and it's just very similar really. It's going to be 1 over theta. Look at your previous example if you're not sure where this is coming from. So 1 over theta d theta equals the integral of minus k dt, and then our final line is ln theta equals minus kt plus c, and again for us that's our general solution of that particular one. On to our final example then. This is a tough enough one, but let's see if we can get through it. It says set up a differential equation for, let's see if I get my pages right here, sorry. Set up a differential equation for the depth of water remaining in an upright cylindrical tank if it is known that the water leaks from the circular base at a rate that's proportional to the square root of the depth of the water in the tank at any time. If the depth of the water drops from 1 meter to 1/4 meter in 1 hour, how much longer will it take for the tank to empty? So we're going to let the depth of the water at any time equal h, and we're going to go for the minus one here. So minus dh by dt. So what does that mean? How does the depth change over time? And we're told that that's proportional to the square root of the depth, so that's root h. Rearranging this, we would have minus dh by dt equals k, and I'm going to put that in h to the power of a half, and then going again, dh by dt is minus k h to the power of a half, taking that over then from there. That's part one. Is it giving us space? Giving us plenty of space, so we'll just go on down the page. Part two. So we know dh by dt is minus k h to the power of a half. We're going to separate out our variables, and then we're going to try and integrate then from there. So the h is to this side, and then the k and the dt then to this side. So I'm going to take this down to the bottom. If with a bit of rearranging, that's going to give me k to the minus a half dh equals the integral of minus k dt. I hope we're okay with that. Adding 1 to the power and dividing by the new power, just take it nice and slowly, is 8 to the power of a half over a half equals minus kt plus c. That of course then is our general solution. Tidying that up, I times top and bottom, so that's not our general solution. General solution is going to be next line down whenever I multiply everything by 2, sorry. But it's going to be, sorry, or tidy it up, just k8 to the power of a half, I haven't times by 2, I've just let the thing divide in, equals minus kt plus c. So what information are we given? If the depth of water drops from 1 meter to 1/4 of a meter in 1 hour, how much longer will it take for the tank to empty? We know a lot of here. We know that when t is 0, h is 1, and when t is 1, h is 1/4. So that's the information we're going to sub in here whenever we're trying to work it out. So let's see. When t is 0, h is 1, and when t is 1, h is 1/4. So you can still see this okay, can't you? Let's move this so there's no issue. Substitute t is 0, h is 1 into this equation here. We will get 2, 1 to the power of a half equals 0 plus c. So that helps us work out our c. So our c in this case is 2. I'm going to go up into our next page. And we're going to substitute that t is 1 and h is 1/4, and that'll help us work out our k. So 2 to the power 1/4 to the power of a half equals minus k upon 1 plus 2, because we worked out our c was our 2 last time. What are we going to have here? 1/4 to the power of a half, so the square root of a 1/4 is going to be a half times a 2, so we just end up with a 1 on this side here. There's a 2, that's a minus 1, so it gives us then a value of k equals 1. So therefore 2h to the power of a half equals minus t, because it's, remember, it's a 1, plus 2. That is then our particular solution. I think it asked then for how long it will take for the tank to empty. So how long is it going to take when tank is empty? H is 0, so let's put our h equal to 0 here, so it's 2 upon 0 to the power of a half equals minus t plus 2. That gives us then the value of t is 2. Therefore the tank is empty after 2 hours. It says how much longer will it take the tank to empty, so therefore it takes 1 hour longer for tank to empty. And that's the end of that one.